Okay, hello everybody. I'll be explaining today the fifth session in the chapter 6 and it would be the last one. I'm Vivane Choykani, so let's start. First of all, let's list our objectives. There are two objectives. The first one is to determine Kr of an acid-base reaction. It means when an acid and the base react together. The second objective is to determine whether an acid-base reaction is complete, which means quantitative. These two words are synonym, or limited. So, about Kr of an acid-base reaction, how to determine it, the first objective. Let's consider a practical example as an exercise in which we have to know how to determine Kr and how to make use of Kr. The first example is the following. In a beaker, we add a solution of NaCN to a solution HF. Here you have to pay attention that NaCN, what do we have? We have Na plus, that is a spectator ion. So we are caring about Cn minus, that figures here on the pKa axis. So Cn minus here, as if it is what? It is a conjugate base or a base for the corresponding acid HCN. And HF, definitely HF is an acid. We have three instructions to be answered. The first one is to write the equation of the reaction taking place. The second one is to determine the constant Kr, which is our objective of this reaction. And the third one is to deduce whether the reaction is complete, it means quantitative or not. So let's start by the first one. As we said, we have Cn minus and HF that are mixed in a beaker. So the reaction would be, definitely we have given about pKa of the two couples involved. So about the reaction, which is part A, as we said, HF will react with Cn minus in a reversible way, given F minus and HCN. Here the reaction can be not reversible as in all cases, because we don't know first of all whether it is a complete reaction or a reversible one. In all cases we consider the reaction reversible first, and then after making the calculation we will decide whether it is reversible or not. Part B, this is our objective, as I said, to determine the constant Kr of this reaction. As any equilibrium, we can calculate the equilibrium constant Kr, because it's a reaction between an acid and the base, multiplying the concentration of the product, exponent definitely the stoichiometric coefficient. But here, as you can see in our reaction, all reactants and products have a coefficient, a stoichiometric coefficient equal to 1. So simply in Kr we will find the product of their concentration here, and the following is for the reactant. Okay, now how to determine Kr? What we have to do is the following. We know from here, we know that the constant A1, the acidity constant of the two couples involved, the first one, it is HCN and Cn minus. It is given by the following relationship as it's seen in chapter 5 or in chapter 6 in session 5. And Ka1 for the couple HFF minus is also given in the following, which we have here, the conjugate base times the concentration of H3O plus over the concentration of the acid. Now what do we have? We have to return again to Kr, and we have to multiply the numerator and the denominator by H3O plus concentration as we did previously. What do we have to obtain? We obtain the following. Here is Kr the same as above, multiplied by H3O plus in the numerator and in the denominator using the red color. Now pay attention to this. I know it's not well seen, but you can follow with me here. What is in blue? You have the concentration of HCN and the concentration of Cn minus with the concentration of H3O plus. Compare these two, these three, which are circled in blue, to the following expression. You will find that what is in blue here is the reverse of Ka2, the inverse, of Ka2. So we can cancel all what is blue here and write instead Ka2. The same to what is circled in green. HF and Cn minus here and H3O plus after all, it is HFF minus and H3O plus. It is the expression here of Ka1. So Kr will become equal to Ka1 over Ka2. Mathematically, we can replace Ka1 by 10 to the power minus pKa1 and the Ka2 times 10 to the power minus pKa2. Mathematically, when this one becomes in the numerator, the minus here becomes plus, so it would be 10 to the power pKa2 minus pKa1. What is pKa2? It is the base, and what is pKa1? It is the acid. Why? This is what we have to explain here. This is the Kr, where we said that 10, it is equal 10 to the pKa base minus pKa acid. Why? Base and acid. Look why. Because in this example, we mixed Cn minus, which is the base, with HF, which is the acid, as it appears on the pKa axis. It means, although I'm considering here the couple Cn minus HCN, but the species present in the beaker is Cn minus, which is the base, because according to the way we are arranging species in on the pKa axis. And this Cn minus was mixed with HF. Although here HF, although I refer to the couple, but the species present at the beginning is HF, and this is why I have underlined here in red, because those are the two species present in the beaker. So this will be the base, and this will be the acid. So in the value here of the base, we will refer to the pKa of this species, and in the value here of the pKa of the acid, we will refer to this species because it is the acid concentrated in this reaction. So as a result, we can write here, as I said, the base here would be replaced by the pKa of the species, playing here the role of the base, and here of the acid, and this is the value of Kr, and this is how we answered the second part of our exercise. Now, what about part C? Part C, they are saying they are using the verb deduce whether the reaction is complete or not. The verb deduce means that we have to refer to what we have worked previously in order to deduce. Here simply Kr allows us to infer whether the reaction is complete or not. How? Kr having this value is greater than 10 to the power 4, so the reaction is complete. Why? Because this is a value taken by chemists to decide or to consider a reaction as complete. Now, after deducing that this reaction is complete, it's not proper to be reversible. Complete, it means a non-reversible reaction. This is why we'll write again the equation written previously as complete and not as reversible, as you can see here. Now let's consider another example. In this example, we have in a beaker, we add a solution of HCN to a solution of KF. Kf, it means K plus is a spectator ion, and F minus will be what? A negative ion, which plays the role of the base. Now, the same three questions asked before will be asked here. Write the equation of the reaction taking place, determine the constant Kr of this reaction, and deduce whether the reaction is complete. It means quantitative or not. What are the species present? HCN and Kf, that will be considered as F minus because K plus is a spectator. And definitely this is the given. So this solution would be for part A, always and always the reaction is reversible between HCN and F minus, as we said here, giving Cn minus and HF. Also here in all cases we consider the reaction reversible first. Now, how to determine the constant Kr? As we worked previously, Kr in this case is equal to the concentration of the product here over the concentration of the reactants here. Again, what do we have to do? The same work. Ka1, it is for the couple HCN Cn minus, that it's given by the following relation as seen in the previous sessions, and Ka2 for the following, for this couple HFF minus, also it is given according to the relation. What do we have to do here? Again, Kr, we have to multiply this relation of Kr by H3O plus in the numerator and in the denominator, and as you can see here, if I will consider Cn minus here multiplied by H3O plus divided by HCN, those three together will be Ka1, and it means yes, it's Ka1 which will be here, and HF divided by F minus of it multiplied by H3O plus, it will be the reverse of Ka2, which will be figured here. So as a result, we can say that it is pKa1 minus pKa2 as we worked here, because this one will be in the numerator and it becomes positive. So pKa basis minus pKa acid. Again, in this example, we mixed F minus, which is the base, with HCN, which is the acid, as it appears on the pKa axis seen previously. Here, look at pKa and the two pKa's. Since F minus is the base, where F minus it is here, so its value is that of the base, which will be replaced here by the base, and this one is for the acid, HCN. So this is the pKa, okay, which will be replaced here. So this is the value of Kr. As you can see, it is equal to 10 to the power minus 6.04. What about the last part in this exercise? It's to deduce whether the reaction is complete or not. As we did previously, the value of Kr will lead us to determine whether the reaction is complete or not. Here Kr is less than 10 to the power minus 4. It means the reaction is practically too limited and it's not quantitative. So here we don't have to repeat the equation written previously, because it is written in a reversible way, as we said, and it is actually reversible, so we don't have to repeat it. So this is about Kr and how to make use of the Kr result in order to determine the reaction, whether it is, as we said, limited or quantitative. Here we have to generalize it. What do I have to say? The equation of the reaction between an acid, any acid H1, and the base A1 of the pair is the following. So here, in all cases, Kr is equal to Ka1, Ka2. But pay attention, you cannot use this one unless you determine it in the way we did it previously. It is equal to pKa base minus pKa acid. Here I have three cases. Although there are a lot of words here, what you have to care about is the following. When the constant Kr is greater than 1, thus the forward reaction is advanced. What does that mean? When the value of Kr, as was said, is greater than just 1, look at these two reactions. We have here the forward and we have here the backward. In this case, the forward one will be more advanced. And what you have to memorize also here is the following. The reaction is said to be complete. It means non-reversible. It means it goes in the first direction if Kr is practically greater or equal to 10 to the power 4, as we said in our example. Okay. The second case, it is the following. Also, a lot of words that you have to read alone, but what you have to memorize is the following. The constant Kr, when it is less than 1, so the forward reaction is limited. It is the opposite case of this one. And when Kr is very small, it's practically very limited when Kr is less or equal to 10 to the power minus 4, also as seen in our example. So these three values, Kr greater than 1, less than 1, greater than 10 to the power 4, less than 10 to the power minus 4, will be memorized by heart as numerical values, and the consequences of them on the reaction also would be memorized. At the end, if Kr is equal to 1, it means we have two couples having the same Ki1, so they will have the same concentration in that case, and the chemical equilibrium will be established. Okay, so this is about Kr. Now, the choice of the predominant reaction. As we said here, when we are mixing more than one chemical species, more than one chemical reaction can occur. But which one is the predominant reaction? The predominant reaction is the one having the greatest Kr, and it is the reaction that determines or that controls the pH. It means other reactions have nothing to do with the pH value. The pH value is controlled or determined by the reaction having the greatest Kr. How to determine the reaction with the greatest Kr? We have to refer simply to the gamma rule according to the pKa axis, where the predominant reaction is the one taking place between the strongest acid and the strongest base. As we said, they can be determined on the pKa axis. And this one also, I will keep it for you to read it slowly alone at home. And what is important is to do the solve to application, to apply after all, or to work the exercises 17 and 18 of the textbook. The solution will be uploaded later, and you have to solve the exercise 2 of the first chemistry session 2013 LS. It is a practical example and typical example about the reaction between an acid and the base as seen in this chapter. Finally, I would thank you for your attention and thank you.